Hello everyone, welcome to Recitation Week 5 for Fluid Mechanics. We will have 6 different questions and they are mostly related to fluid kinematics. So let's get started with the first one. This is question 4.28. Here, the velocity of water flowing the nozzle shown is given by the following expression. So we have a nozzle here and we have the velocity of this water. And we have this expression that we are going to use for velocity. Here the velocity is in feet per second, t is time in seconds, and here we have x, which is distance along the nozzle. So this is x. We will have L, which is the length of this nozzle, which is 4 feet. When x is equal to 0.5 L and t is 3 seconds, what is the local acceleration along the center line? And what is the convective acceleration? And we are assuming that we have quasi one-dimensional flow. So this means that it actually allows flow properties in both directions, but we are simplifying that and we are assuming that these properties can be treated as one-dimensional along the flow path. So in other words, we can just say one-dimensional flow. Okay, now we can focus on the question. So we have velocity 2t over 1 minus 0.5x over L square. As the next step, let me write the definition of acceleration. So we have a here, we have derivative. So and we will have partial derivatives here. This is for x direction, this is for y direction, and the last one is for z direction. And here, this acceleration is actually a combination of two accelerations. One is local acceleration, and the next one is convective acceleration. And also in the question, we are required to find both of these accelerations. So here we need to eliminate some terms. For example, we will not need these two terms because we only have one direction, which is x, and we don't have y or z directions. Therefore, we are keeping only this one as the convective acceleration, and we are keeping this one as the local acceleration. So let's first start with local acceleration, because the question says that we need what is the local acceleration along the center line. So as local, we only have dv over dt. And here we can write this in this form. So partial derivative of velocity over t, which is time. And we can write the expression for velocity. And the next step is calculating the derivative of this equation for t. So let me write this. So here we have 2. over 105x over L square. So the only term with t is 2 over this definition. So we can directly use this part as derivative of this entire definition. So this is derivative of velocity for t. And from here, we can substitute what we have. So we have t, sorry, we have 2, we have 1 minus 0.5. And if you look at the question, we have x, which is equal to 0.5 L. So we have 0.5 L over L squared. So here, these L's will cancel each other. And the remaining will be 2 over 1, 0, 1 minus 0.5 times 0.5 square. And from there, we can get local acceleration as 3.56 feet over square second. And the next step is calculating the convective acceleration. And let me use AC. And since we eliminated these two terms here within the convective acceleration definition, we only have this term. So AC is equal to U dV over partial dx. And here, this U is actually velocity term, and since we are only dealing with one direction, we can directly use it as V. So let me write V partial V over X. So if we substitute all the values here, we are going to get 2t, let me see. So we will use that. We get 2t 105x over L square times we have partial d over dx, and again we are going to write velocity because of this term here. So we have 2t over 105x over L square. This time the calculations are more complicated because this time we need to take derivative for x. So we have x here, and we are going to keep this as it is because it's just a velocity term at the on the left hand side of this term. So let me write keep this as it is. Now let me write the calculation of this partial derivation. So here the main focus is x. So let me write this in another form. So this is actually 2t times 0.5x over L to the power of minus 2. So we are actually writing that term in this form because we can do that calculation. We can do calculations easier. So we have 2t here, which will not be changed, times, and right now we need to get derivative of inside of parentheses and derivative of entire term. So we will have minus 2 coming here, and the derivative of entire parentheses, and here we will have minus 3 and this is actually coming from once we have a parenthesis and let's say it has power of n, the derivative of this equation will be n ax plus b to the power of n minus 1. So we are just following the same, and plus a, which comes from here. And of course we are assuming that this is partial derivative of this term. And now we can take derivative of inside. So we have 0.5 over L. And this is also coming from here. The coefficient of x is 0.5 L. So it will be the derivative of 0.5x over L. And let me modify this result. So we already had this term, which we said keep as it is. So we have 2t over 1 0.5x over L square times this entire term. So we have 2t minus 2 0.x over L and minus 0.5 over L. And here, let's see what we have. We have 2t, 2t. We have 4t square over over L and we have we have this term with power of minus 2 and with the power of minus 3, so that in total we have this term of power minus 5. And here we can actually substitute actual real values. So we have t, we have L, and we have x. So let's see what we have. The t was given as 3, x is 0.5 L, and L is 4 feet. So we have t as 3. We have square of 3 over 4. Because this was 4, this was 3, and this was 0.5 L. So if you continue writing, 1 minus 0.5 times 0.5 L over L to the power of minus 5. So they cancel each other, and we also remove this. And finally, this is going to give a value because we don't have any variable here, like x, l, or t. So this is going to give 37.925 feet over square second. And this is the convective acceleration. Sorry. Now we are solving second question. This is 4.34. So here we have water with this density stands at a depth of 6 feet in a vertical pipe that is open at the top and closed at the bottom by a piston. So this distance is 6 feet and it is open here and closed at the bottom, and this is a vertical pipe. And we need to find upward acceleration of the piston, which is necessary to create a pressure of 8 pounds per square inch gauge immediately above the piston. So first we can assign some numbers to simplify the solution. So let's say we have bottom, and let's say this is 0.1 and this is 0.2. So at 0.1 we have pressure as 8 psig, and Z1, which is the elevation, is 0 feet. And since this is open atmosphere, we can say that pressure is 0, but the elevation will be 6 feet considering this distance. Here we need to find the upward acceleration. So here you can make an assumption. So upward acceleration. So we are taking upward acceleration as positive because, as you will see later, we will have minus on some sides. I mean minus on the left side or right side. So that the only thing with this sign is assigning the direction. So upward acceleration means we will have positive, and it means the surface minus piston. So this means that if you calculate the change, we will get the surface as final and piston as the starting point. So as we always do when we use change in something, we are usually doing that, final minus start. I think you will get that better in 5 minutes actually. So here we need to use Euler's equation, because Euler's equation tells us that pressure difference between 2 points in a fluid that's separated with a distance L, which is 6 feet, can be calculated by density times acceleration. So actually this equation directly points Euler's equation, and we can solve the question using Euler's. And you can get this from your slides. So Euler's equation is equal to d over ds So this is density. Actually, let me write S because we are using S. Sorry, we are using S as the distance unit, distance definition. So we have AS, we have DS. So here, this says that this is the change with respect to S distance. So we can use delta instead of this partial derivative. So let me write let's say, so we also have minus here. So we have delta plus pressure change. So total pressure, because this also means pressure because it is specific weight times elevation. This is equal to actually let me start from here. So we can modify that in this shape. This is equal to minus acceleration times delta S. Let's continue with the question. And later we can modify this, and actually we can move this negative sign to the left. This is just to verify the direction, and we will see that impact at the end. So we have minus delta P plus gamma Z equal to rho A S delta S. So this means that change in pressure, and as I mentioned, delta is final minus starting. So in our case, it is 0.2 minus 0.1. So we can say that this is minus 0.2 minus 0.1. And this is coming from this side. And additionally, we are also doing the same for this part. So this is delta Z Z2 minus Z1. So here we just took the delta, we took just the change of P2 minus P1, and since this is a constant, we can use it outside of the parentheses, and then we get Z2 minus Z1, and this is equal to density acceleration times delta S, which is change in distance. And let me write what we have. So we have minus P2 was 0. We have 8 PSIG. Actually, let me write this pound over integral. And since all terms are in feet, we can actually convert this to feet. So let me write 144 inch square over 1 square feet. So this is for the first part. And next we will have this second part. And we have minus. We have specific weight, which is 62.4 pound force over cubic feet. So we have 62.4 times the change in distance, because this is going to be 6 feet. It is because we had z2 as 6 feet and z1 is 0. So let's say this is 6 feet. And this is going to be equal acid of water, which is 1.94 slug cubic feet. Times delta S is 6 times acceleration. And from there we can get acceleration as 8 psi g times 144 inch square over feet square minus 62.4 times 6 feet over the right hand side times 6 feet. And this gives upward acceleration as 66.8 feet over square second. So as I mentioned, we took upward as a positive, and since this generated a positive acceleration, this means that this is upward direction. So the location of this negative sign is actually not very important, because at the end you are going to see the impact of minus. So at the end we assigned positive for upward acceleration, so this means that surface minus piston, so final minus starting, will be positive. And after all these calculations, we calculated acceleration as positive, so this is upward acceleration. Okay, this is question 4.37. We have a liquid with a specific weight of 100 pound force per cubic feet in the conduit, which is here. And this is a special kind of liquid that has zero viscosity. The pressures at points A and B are 170 and 100 psf. So let me write this. We have PA as 170 pounds per square force, and we have PB as 100 psf. Pound, and this is pound force over square feet. So which one or more of the following conclusions can one draw with certainty? We have four options. The velocity is in the positive L direction. The velocity is in negative L direction. The acceleration is in the positive L, or the acceleration is in the negative L direction. So here we have a liquid flows flows through a conduit here, but we don't know its direction right now. Again, this question is actually similar to the first one because we are using Euler's equation. So let me write Euler again. So this time for the distance we are actually using L. So I will stick to this. We have P plus comma Z equal to density acceleration through the length. So this gives minus partial derivative of P over L and minus, again, specific rate is constant. We have C over L. This is equal to rho times acceleration. And let's continue with the first term. So as I mentioned, this means change with respect to L. So this says PB minus PA over L minus specific weight Z over L. Okay, so let me continue from here. So PB is 100 and PA is 170. So this means we have 100 and 170 PSF over L. So this distance between these 2 points is 2 feet. So let me write 2 feet. Instead of PSF, I can directly write pound force over square feet. And this gives minus 35 lbf over cubic feet. And on the other hand, we had this term so to find this we need to look to shape. So let me move this here. So let's say we have Z, we have Z here, and we have 30 degree. So this means that we have sine 30, which is equal to Z over 2. So Z will be equal to 2 sine 30. So this means we have 2 sine 30 over 2, which is feet. And what we get is sine 30. And this is actually equal to 0.5. So let's write everything together. We have minus 35, we have 0.5 times specific weight, and we have density times acceleration. So acceleration would be equal to, and if we divide all of these terms by density, we are going to get 1 over density we have actually minus sign here, negative sign here. So it is going to be positive 35. So let's say we have 35 plus, minus, we have 1 as the specific weight, times 0.5. And from here we can get 1 over density equal minus 15 lbf pound force over cubic feet. So in other words, we have minus 15 pound force over cubic feet and density. So the final answer will be minus acceleration. So the only option we can choose is the acceleration is in the negative L direction, because we have negative acceleration. So in this question we need to use Bernoulli, and since you already know from the course, but let me remind you again. Bernoulli equation comes from applying Euler's equation to steady flow along a streamline. So this is the important thing to differentiate between Euler's and Bernoulli's equation, because steady means there is no change with time. And in this question it says the mean velocity is 5 feet per second. So this means that the velocity is not changing with time, so that we have a steady flow, and this means we can apply Bernoulli's equation. And this was upstream pipe, and this was the minimum area. So let me call this surface as 0.2 and this one as 1. So here we can write Bernoulli between 1 and 2. So here we can write the Bernoulli's equation, which is P1 plus gamma Z1 plus rho V1 square over 2. This is equal to P2, which is pressure, specific weight times the elevation, plus density V square, velocity square over 2. And from the problem we can see that the velocity in this pipe is 5 feet per second. So this is 5. And let me modify this equation again. We have rho V2 square over 2. So we are leaving this term alone, because what we need to find is velocity at the minimum area, or in other words it is V2. And this is equal to rho V1 square over 2 plus P1 plus gamma Z1 minus P2 plus gamma Z2. So here there's a confusion about the wording, because it says delta Z is 6 inch, but it actually doesn't mean the Z1 minus Z2 is 6 inch. You cannot say that, but this distance is actually distance in piezometric head. So this is the drop in piezometric pressure. So let me clarify it here. We have delta Z as 6 inch, and this is the drop in pressure or piezometric head. So what we should understand from piezometric head, this is P1 over gamma plus Z1. So here, if we divide these terms by 1 over gamma, we will get V2 square over 2G equal to V1 square over 2G plus P1 over gamma plus Z1 minus P2 over gamma plus Z2. And as a note, this is actually coming from gamma equal rho times gravitational acceleration. So here these terms will cancel each other. So we will get 1 over G, which is here. So the delta Z, which is the difference in piezometric head, is 6 inches, and this is actually 0.5 feet. And since we already know the V1, this is 5 square over 2 times 32.2 feet per second square. So V2 square over 2G is equal to this term plus 0.5. So V2 will be equal to 7.56 feet per second. Okay, we can continue with question 4.50. Here we have a glass tube which is inserted into a flowing stream of water with one opening directed upstream and the other end vertical. So let me clarify what we have. We have a glass tube which is shown here, and this is inserted in a flowing stream. We have this flowing stream and one opening directed upstream. We have opening directed upstream, and the other end is vertical. So if the water velocity, which is VA, is 6.6 meter per second, how high will the water rise, or we need to find h here. So in page 129 and 130, you can find more information about stagnation points. So this is actually called stagnation tube. So at this point, let me S point, velocity is 0, because you can see an example here. So we have this tube, and at this point, as you can see, we don't see any velocity, and here we will be 0 at this point only, which intersects with this flowing stream. And also we have through stream here, which we can mark like this, through stream. And now, to solve the question easier, I'm going to assign some numbers to specific points. So here, the point 1 is free stream. Second is stagnation point. And 3 is the end of this vertical section. So we need to find rise in this vertical leg above water surface. And again, we are going to apply Bernoulli's equation, because there is no change in the velocity, and this is just directly given without any change in time, without mentioning any change in time. So let me start writing Bernoulli's equation. So first, Bernoulli between 1 and 2. So I forgot to write, this is point 2. So between Bernoulli point 1 and 2, we have P1 over gamma V1 square 2G plus Z1 is equal to P2 over gamma V2 square 2G plus Z2. And don't get confused with this form of Bernoulli. So we can either write these in this form, or it can be something like this. Something like this. The only difference here, we are only dividing the entire equation by specific rate. So eventually they are actually same. And here we are going to eliminate some terms. So since they are at the same level, we can actually discard elevations. And second one, as I mentioned at the beginning, we have this point 2, and velocity was 0. So we will just remove that, because it is 0. And finally, what we get is P1 over gamma plus V1 squared 2G is equal P2. And let's say this is the first equation we have. Here we can actually find a value for P1 over gamma. So let's focus on the point of 1. So this is point 1. And above, onto the surface, we have a depth. And let's say we have this depth as d. So the pressure at this point will be just specified times d. So actually write P1 is equal to specified times d. So this makes delta as gamma d over gamma, and what we get is only d. And if we substitute this equation here, we will get d plus v1 square over 3g is equal to p2 over gamma. Something for p2. So let's see what we have. We have 0.2 and above this point we actually have d and also h. So we shouldn't get confused about what we have above this point. So of course it seems like we have only this surface, which is d, but since this is already in this glass tube and it's actually going up to this point, so pressure at point 2 is specific times d plus h, because the water column is d plus h over 2. So let's say it is gamma h plus d. And again, from this equation, we'll get d plus 1 v1 square over 3g, 2g is equal to h plus d, because this is gamma h d over gamma. Okay, so let's see what we have. And also, as you can see, we have d on both sides, so they will eliminate each other. So v1 square over 2g is basically equal to h. And v1, or actually as stated in the question, va is 6.6. So this is actually fluid stream velocity, or this one's v1. So h is equal to 6.6 meter per second. Square over 2 times 9.81 meter per square second, and this gives h as 2.22 meter. So we have h as 2.22 meter. Okay, the last question is 4.70. The velocity components for a two-dimensional flow are u and v as they are given, where c is a constant, and we need to determine if the flow is irrotational. So from your textbook you can find this information. When the vorticity is 0, or we have this 0, we will get flow irrotational. And in other words, it means partial derivative v with respect to x is equal to u over y, and you can find this in your course slides. So when we meet this requirement, our flow will be rotational. So let's see. So first of all, let me start with v partial derivative of v of 2x. So this means that we have this cy over, and derivative with respect to x is equal to let me write this in this form. And its derivative will be equal to, we have minus 1 cy, also derivative of inside of parentheses with respect to x, so we will have 2x, and finally x squared plus y squared over minus 2. And similarly for u over y. So this time we are going to get derivative with respect to y. And so this means now we will use this u. Cx over y squared plus x squared. So its derivative will be cx, because this has nothing to do with y. The only y is here, so we will have 2y and also we will have minus 1 here times this term's derivative, which is x squared plus y squared to the power of minus 2. So we can also use this as v over x, u over y is equal to 0. So let me write everything we have. We have cy 2x minus minus cx 2y x squared over y squared over y squared to the power of minus 2. So this part will be positive because we have minus and we have minus here. So we can write this in c 2x y. Also c x 2y. So as you can see, basically they are same with each other. We have cx 2y, we have cy 2x. And since we already have negative sign here, and this is positive, and they are equal to each other, this will be equal to 0. And this means flow is irrotational.